Hello, Science 30s. I did make a video about this earlier, but the microphone was muted, which made for a horrible recording. So I'm going to go over this again. It may not be as long as the first one because I'm just going back over the stuff that I studied or that I showed you. I will leave the first video in case you want to see my steps, but oh, the audio was just horrible. So sorry about that. Anyway, energy is the capacity to do work. And I had highlighted here the different forms of energy, and you should be prepared to address them. These units here, terajoules is as high as we go on your data booklet. Petajoules and exajoules, I'd never heard of those before, but they're times 10 to the 15, times 10 to the 18, whatever. Um, just bigger and bigger amounts. Okay, but those letters are found on your data sheet, and in fact, I should probably find that quick so that you can. Um, so that you can look at some of that. So the, uh, yeah, here it is right here. So on your formula sheet here, I'm just backing into it. See here, all of these symbols here, tera, giga, mega, that's as high as it goes. Just be, if you if you see a prefix you don't know, look on your formula sheet. And if it's not there, then they need to explain it. So, because like, petajoule and oh my goodness, exajoule, those are insanely big units of energy. The calorie is an interesting one. If any of you go into nursing or nutrition, you'll study that at length. Um, the food calorie is the one that we typically talk about in, nutrition and other classes, and it's just different by a factor of 1,000 compared to a calorie. We really will just talk about it. You won't have to do any calculations with that. BTUs is cool. British thermal units, usually measures of like furnaces and barbecues. But the kilowatt hour, that's when we've already used. And if you remember, I already highlighted that energy equals power times time. We use that calculation when we're determining, what power companies charge you and stuff like that. You do need to be familiar with the vocabulary per capita, as I highlighted here, and as well as gross domestic product. When we're talking about energy and we start looking at other countries, we make those comparisons. Uh, and the first one is definitely called energy intensity. Okay, so I kind of highlighted this here already. It's a measure of a country's energy relative to its gross domestic product, or its total market value of goods and services produced by a country in 1 year. Okay, so energy intensity, here's a nice formula for it. I mean, whatever, it's just a ratio, energy over dollars. In this example here, it compared Kenya, Sweden, and Canada. And what are their energy intensities? Well, I just did it quick for you. The energy use in Kenya, 0.2 exajoules per 0.1010 trillion US dollars. Okay. So that actually comes out to 20 exajoules per dollar or per trillion dollar. And Sweden has 7.4 and Canada has 18.3. So what's interesting here is it looks like developed countries use less energy, but that's not necessarily the case. I mean, Canada uses a ridiculous amount of energy compared to Kenya. Almost 10 times, not quite. Or no, more than 10 times, sorry. Um, but the rationale for a lot of this is what you need to know. More like the more developed a country is, actually, the more energy it does use. And Canada is known for producing products that require energy to make. So, oil and gas, natural resources, it takes a fair bit of energy, for large machinery and equipment and storing and refining and everything else to make our products. So we're very wealthy, but it also requires more energy. And so anything you can do, if Kenya has a high number too, 20 exajoules per trillion dollar produced. But what you have to realize is Kenya potentially doesn't produce that much, and they don't. Look at their GDP, it's like 0.01, okay, compared to 0.753. So yeah, Kenya's not producing very much, but they're consuming energy. So per dollar of GDP, they're not, they're making, or sorry, they use quite a bit of energy per dollar that they make. So if you make more money, so on. So anyway, yeah, so it's not necessarily automatic that developed countries use less energy. In fact, in most cases, they don't. I mean, the US is actually the leader on that. So you do need to know these 5 factors affecting energy use. I've already underlined them. I guess I could kind of clear those off there. Climate. Yeah, there's just a direct relationship there, and it's mostly the extremes in temperature, okay, that are a factor, and I highlighted that here. So yeah, if you're in a cold climate, you're going to use energy because you're heating buildings. If you're in a warm climate, you're going to use energy because you're cooling buildings. And yeah, the perfect storm is if you have a cold winter and a hot summer, which that has happened, that can happen. And so yeah, then you're using energy to heat buildings, and you're using energy to cool buildings. So the extremes in climate affect energy use. And unfortunately, due to climate change, we've seen more and more extremes. So the amount of energy use is not going down, that's for sure. Another one is activity. And you can measure activity in a bunch of ways. I listed those there. High economic activity corresponds to high energy use. That should make sense. Okay, so if there's lots of activity, we're going to be using lots of energy. And probably a really obvious one is population. Wow, if you're going to try and raise the standard of living for everyone in a country, if there's more people in the country, then you're going to need more energy to raise that standard of living for everybody. Okay, so the real risk is, if you don't plan as a country, you'll just kind of, grab energy, like from the environment, and you might just kind of get what you need quick because you want it and need it. But if you don't plan well, you can really damage the environment. And so that's kind of the educated approach. So the fourth one is energy intensity. We already talked about that, how much energy per dollar of economic output. High energy intensity, you have, large equipment and transport for, like example, for mining coal. That's definitely Alberta in terms of what we do, and you'll see that in a graph here. And then low energy intensity, if you're making something that doesn't require a lot of energy, but you get a lot of money out of it, then that's good too. So anyway, we need them all, though. We really do. So the last one is energy efficiency. Now, I did say see your data booklet. I'll maybe just pull that up again quick. In your data booklet, sorry, I'm kind of scrolling through. I think it's page, where is it? It's not that one. I think it was right near the front. Yeah, right here. Sorry, there it is. So it's the second page. There's percent efficiency in case you need. I mean, you guys have done that probably in other science classes. It's always output over input. You see it right there. Percent efficiency is energy output over energy input, or power output over power input times 100%. Okay. But yeah, you're going to have to use that. I don't think it's too bad of a calculation. Here it is. I wrote it up here again. And yeah, it's worth noting. I mean, in Canada, we have what's called Energy Star. The government has expectations for all kinds of products. And if you purchase a product and it has that Energy Star on it, it means that it meets certain levels of efficiency, and that's a good thing. It'll save you money in the long term. Really, it does. Efficiency is a big deal. You don't want to ignore it. If you're running a business and you don't pay attention to it, you can sink yourself with unnecessary costs. You want to be as efficient as possible. And trust me, when money's driving you, you're going to do it. Anyway, you can see all these devices for input and output energy. Most of the input energy is electrical, except for the car engine. And the output energy varies, because for light bulbs, obviously you want light. Car engines, you want movement. Actually, an oven, you just want heat. So if you're making heat, actually, you can have very efficient systems because in the process of making heat, you produce waste energy as heat. And so, yeah, you're making heat. No surprise here. Waste energy, I circled this. Almost everyone has thermal or heat in it. Okay, that's just, those are in any system or any process, you're going to definitely be wasting heat. Okay, so I did a couple calculations here. You have energy efficiency. Sorry, I kind of blocked these out, but if you've looked at it here, just know if you have input and output, it's easy to identify. The input is always the biggest number, and the output is the smallest number, because you can never get 100% efficiency. That's due to the law of thermodynamics, or law of conservation of energy. we'll highlight that at the end of this. Okay, so yeah, in this first example, the efficiency was actually output over in. So you'd go 55 divided by 200, you get 27.5% done. And the second one, if you are 20% efficient, what's the output energy from a kilogram of gasoline if you have 44.5 megajoules of chemical potential energy? Well, you can see here, you set that up, 20% is equal to out over in. I actually made a mistake when I first did this. Let me just clean that up. So the point is, yeah, the 44.5 is the input energy, and the output is what we're trying to find. And when it's only 20% efficient, yeah, we're only going to get 8.9 megajoules of useful output energy. Okay, so yeah, an efficiency calculation, I don't think they're horrible. Just take your time when you see it and get things in the right spot. I had to mention this because at the high school, I know all the Science 30s, most all of you I think are graduating, so you won't see it. But since the school's been shut down, they've worked on replacing all of the kind of the long fluorescent lamps, the fluorescent tubes that are in the lights. They've replaced them all with LEDs, and it looks awesome. They're kind of a softer light. LEDs can be really bright and harsh, but these are nice and soft. But they are a little bit brighter than the fluorescent lamps, and it looks awesome. But it's a no-brainer. I mean, almost all lighting is LED already. I mean, all the new cars you have now, everything's LED, including the headlights. Just everything's LED. LEDs are quick, or they've easily proven over the years to be much cheaper. They last for years, like 5-10 years sometimes, and they're a lot more efficient. So in terms of efficiency, I just threw these numbers up here. Incandescent light bulbs are like 2% efficient. Most of their energy is lost as heat. The CFLs are 10 to 12%, a little better. They still produce a fair bit of heat, but they actually don't cost as much. And the LEDs, wow, yeah, they cost almost nothing. The technology's improved that way. So, and I've never really got a hard percentage on that. I thought they were 20 to 30%, but it really varies a lot. So, worth mentioning, our economy, my goodness, fossil fuels make up half of our exports in terms of what we ship out of our province. And energy companies pay what are called royalties. You've probably heard that in your social classes. It's money to the government that's a share of the profits made. And that makes up about a third of our total revenue. That's a huge chunk of what our province makes of our GDP, I guess you could say, if we were doing it for just the province. So but as a result, we are the most energy intensive province in Canada. And take a look at this. Okay, all the provinces are listed here in terms of how much energy they consume, terajoules per person, okay, or per capita. And yeah, Alberta is just kicking butt here. Not that it's necessarily, it doesn't look good. It's like, oh man, we're consuming a lot of energy, but we are making products that are that other countries need, not just Canadians, but other countries. We export to other countries, and as a result, we're one of the wealthiest provinces in the country. And so we are super lucky that we've got hardworking people and the infrastructure to be able to do this kind of stuff. And hopefully we can continue to do that because it's very beneficial. So that's the first section, really. It's all of that theory plus efficiency. The second section is just a review of fossil fuels and the history of where they come from. So let's just dive into this quick. You can see this graph if you were to interpret it. Sorry. For thousands of years, humans just burned wood for energy. Actually, I'm not sure the history of charcoal. I noted that charcoal is wood that's actually kind of baked at high temperature in almost the absence of oxygen, so you don't see flame. But if you've ever used charcoal briquettes or just charcoal in general, it's a really effective and concentrated heat source. It's just a little tricky to make, and so as a result, it's not the easiest fuel to get at. Over time, coal became the dominant fuel source, especially in the early 1900s. In fact, in our province, that's when we started mining like crazy. There's a whole bunch of mining towns in our province. If you paid attention when you drive through them, Coaldale, Colehurst, just a subtle hint there. But yeah, all over the province, we have so much coal. It's insane. Yeah, this number here, the estimates are around 620 billion tons of coal, and that's apparently coal that's easy to access, like surface mining. We just got to scrape off the topsoil and get down to it, and it's right there. So because though it takes millions and millions of years to make coal. If you're familiar with the process, it's dead plant and animal material that's been buried under sediment and under pressure for millions of years, and it becomes coal. So that's why we call it a fossil fuel. Okay, so not too surprising though. I'm sure you've heard of that. In our province, though, surface mining is pretty ugly. I mean, you can see this picture here. We rip up the ground and kind of level mountains practically, and to get at the coal, we make a huge mess. Alberta does have high standards, which are followed for the most part. There's a couple exceptions, but mostly mining companies, after they've extracted all the coal, they repair the land, and that process is called reclamation. So hopefully, in most cases, it looks something like this. Obviously, it won't be exactly the same, but at least you can, regrade things and put grass down and stuff like that, and maybe, get some clean water in certain areas. So that's coal, though. Okay. But the real moneymaker is petroleum. Okay. When we use the word petroleum, we're referring to basically crude oil. Okay. And but in history, basically the coal started the Industrial Revolution, if you remember that in your social studies, in the early 1900s. But petroleum kind of kicked in towards the end of the First World War, and definitely by the Second World War, as kind of the leading source of energy. And petroleum is incredible. There are so many products we get out of that. Natural gas followed that too, and we'll look at it. In our province, we have some of the largest oil deposits in the world. They rival places like Saudi Arabia. It's insane. The only problem with our sources is that they are mixed with sand. Okay, they're mixed with sand and rock, hence the name oil sand. So I've never actually been to Fort McMurray. Maybe some of you have. It's famous for being one of the largest cities, smack dab in the middle of the oil sands, Athabasca oil sands. There's some in Peace River and Cold Lake area. So we still have to access it with normal surface mining techniques, but using water and a bunch of chemicals, we can separate the oil from the sand. It's kind of an ugly process. You make a big mess doing it, and a lot of environmental groups have been really critical of the process because you have these tailings ponds that birds land in and then they die because it's just toxic and yucky. And so the industry has had to kind of step up its game in terms of trying to be as environmentally conscious as possible. And there's lots of regulations in place to try and enforce that. But man, it's been a huge boost to our economy to have this stuff. And here's why. Look at this. This column here is called a fractionating column. And what you do when you get that crude oil extracted from the sand, then you heat it up. And in this boiler, look at all the products that come off of this. It's crazy. And I like this diagram because it shows you the number of carbons. So the heaviest kind of product is anything around 70 carbons chained together. That's huge. Okay. And you get that many carbons together and you have a very heavy and thick, black, dark product. And that's what asphalt is made from. Okay. Bitumen is the name of the material. But yeah, we make shingles out of this stuff. And then you can see as you get lighter and lighter, you get more refined gasoline products. So look at that. We go from lubricants to diesel to kerosene, jet fuel, gasoline, all the petroleum products, all the plastics come from this stuff here in this top level. And then way at the top here, we get natural gas and other products. So all of that comes from crude oil, and it is no surprise that that's why we are so hungry for oil. Like so much of our lifestyle and products we buy, things we build our homes out of, come um, from this stuff. So I kind of highlighted that here in this little compression of what goes on in the oil sands. I did mention natural gas. Natural gas is mostly methane, but it's also a mix of these other guys, ethane, propane, and butane. That's why it's kind of a mix. Um, but natural gas definitely forms underground as well. The temperatures just have to be a little hotter, I believe. But we use that to heat our homes. It's awesome. Okay. There's another form of methane called coal bed methane. It's just methane that's actually been dissolved in water that's intermixed with the coal. So instead of venting that and just wasting it, companies are grabbing it, as they should, to be more efficient. And methane hydrate, that's just frozen methane. It occurs in, obviously extremely cold temperatures and under lots of pressure. But if you get it frozen, it's either frozen or gas, but we can grab it. So overall, though, this is the big one. Fossil fuels are considered non-renewable hydrocarbons. Okay, so the reason, I mean, they're really valuable and we're going to use them, but they are a finite resource, and we'd be unwise if we just planned on having them be around forever. So we'll get into that later, because I really believe that solar energy is going to eclipse all forms of energy in the next 10 to 15 years or whatever, and we'll be using the sun's energy to get everything we need. So but you should know the word bias. You'll see this a lot as you get into university. Bias is a preference for one particular point of view that interferes with a neutral or objective point of view. I really like that definition. Okay. So everyone's got bias. You have to accept that. And if you do, then you'll be a wiser person and a wiser contributor to problem solving. Okay, because everybody has a bias and depends on your point of view. So that's worth mentioning. So that's the second section. Okay, the last section that I got to was harvesting chemical energy, and it goes into combustion, but a little bit of the math behind it. Okay, so we've already studied combustion. That's where in the presence of oxygen, a material will release energy. And when we talk about temperature is actually a measure of the average kinetic energy of atoms or molecules in a substance. Okay, so heat is the transfer of energy from molecules or atoms at a higher temperature to those at a lower temperature. Okay, that's what we would say heat is. And I know those definitions probably blend together. Hopefully this little example will help you separate them. Let me just erase this so I can talk about it. So the point is that in a typical engine or an internal combustion engine, you have particles of gas. Here, let me just erase this so you can make sense of this. So there's particles of gas in here, okay, right in here, and they are there at a low temperature. But they have high chemical potential energy because those gas molecules have they have a whole bunch of bonds between their molecules, and if you break those bonds, you can release a whole bunch of energy. So in this first picture here, we have low temperature, low kinetic energy, okay, and that's actually what we should note here. This is kinetic energy, but this we have a high potential energy. Then we change everything and we just trip a spark plug, which causes combustion to begin. And what we're left with afterwards is a really high temperature. So we have high kinetic energy. Okay, the particles are really moving now, and they're moving and bumping around into each other, so they exert a huge amount of pressure and they ram that piston down and drive the engine. Okay, but after combustion has happened, now you have a lower chemical potential energy. The potential energy has now been lost, or really it's not been lost. I should be careful saying that. It's been converted into kinetic energy. Okay, and then obviously with the piston in the system, as it drives down, it will replace the gases and do it all over again. And that's kind of the genius behind an internal combustion engine. So this is the process right here. This change in energy during combustion, you start with high potential energy, and that drops down to low potential energy. Okay, so you see that there in red, you go from high down to low. For the kinetic energy, you start low and then it goes high because you now produce kinetic energy, or um, an increase in the temperature. Okay, so the that process can be mapped here in this drawing here, and I emphasize the term exothermic. And if you've taken chemistry, you remember that term. Okay, exothermic means that the reaction gives off heat. Okay, or it produces heat. And on this graph, it shows the potential energy on the y-axis. Okay, so not kinetic energy. This is just showing potential. So the potential energy, it's high in, this is octane, by the way. So octane is burned, and you produce carbon dioxide and water. We always produce carbon dioxide and water for these, so hopefully that's a little easier when you're trying to process this. But the products have less potential energy. They don't have as much potential to produce energy as the original octane. So their final potential energy is low. But as we saw before, that energy just didn't disappear. It became kinetic energy or heat. Okay, so there's a bunch of symbols here, and I don't want you to trip on them too much. They call it the heat of combustion, and it's really a delta little ch with a degree. The H is heat, C is combustion, delta means the change in. You'll see that in the formula. So really, the only formula that you need to practice is the one in the data booklet. Actually, yeah, let's just look at that right now. So, oh wait, I think I buried it. Where is she? Yeah, okay. So in your data booklet, you have to skip ahead to, I think it's page 5. Okay, there's some electrochemistry, boom. Okay, here we go. So where we're headed to is what are called standard heats of formation. And they're all listed, they're listed here, and it's this delta F H degree. Okay, so F stands for formation, C stands for combustion. I'll explain that in just a minute, but if you remember these, then we should be just fine. But this is the formula right here that involves reactions, okay? And it's delta R is really the change in the energy from the reaction, okay? So that's equal to, and you'll see it in the thing, the sigma means the sum of, N is the number of moles, but it's basically the sum of all of the energy that the products contain, and we subtract from that the sum of all of the energy of the reactants. So it's the products minus the reactants is a simple way of looking at it. And I'll pull that up again in a second. So, oh, yes, what's worth mentioning here is a calorimeter. Calorimeter is just a device that we use to measure this energy, how much energy is released, how much heat is released when you burn something. The best way to do it is submerge it in water, and that's what this is called. It's called a bomb calorimeter, which is kind of a cool name. But inside this little steel bomb here, you put the reactants, okay? So if you're doing some food chemistry, you could put, I always think of peanut butter or whatever. You could put some peanut butter in this steel bomb, make sure there's oxygen in there. You get some electrodes that run in there and you light it on fire. You burn it, okay, to try and release all of the possible energy that is contained in that food source if we're talking about peanut butter. The heat is radiated outwards. I kind of showed those little squiggles. This stirrer works to move the water uniformly so that the thermometer gets a good reading. But yeah, I mean, this thermometer is going to heat up. It's going to measure a change in temperature when you burn a food item in this bomb calorimeter. And it's obviously insulated. You can, like the dark purple around it or whatever is insulation. We're trying to contain the heat that was released so that it can be measured instead of just dissipated to the surroundings. Okay, but that's a calorimeter, and yeah, it's called that because it's measuring calories. That can be a little problematic in lots of ways, though, especially for large samples. Another way to do this was kind of conceived by a man named Germain Hess, and I mentioned his name down here. It's called Hess's law, and all it is he said we could consider how much energy it takes to form the products, not to break them apart, not to burn them, but how much does it take to form the products, and also the reactants. And if we use that measurement, then that would equal the amount of energy that is released. So it was a really kind of a genius way to look at this problem, is to look at the formation, how much energy it takes to form these products, because the energy that it takes to form them will equal the amount of energy it takes to break them apart. I mean, that's simplifying it a little bit, but if that helps you kind of understand it. So what we do is we look at the difference in the chemical potential energies between the products and the reactants. That's really all we're doing. What's worth mentioning here, pure elements have a standard heat of formation of 0, and I put oxygen. In all of these combustion reactions, oxygen has no chemical potential energy as a pure element, so you don't have to worry about that one. Okay, so again, here was the expression that we saw in your data booklet. It's basically it's the sum of all of the products minus the sum of all the reactants, or as I wrote there in red, it's the sum of the final products minus the initial, final minus initial. Okay, so again, sigma, these symbols here, this is the Greek letter sigma. It means the sum of. You might have seen it in some of your other math classes. N, though, is the amount of moles, and you know what? It does need to be a balanced equation. Sorry about that. Most of the equations I'm going to throw at you are already balanced, but if you have to balance it, do it, okay? Don't miss that. And then anyway, the rest of the formula kind of cascades out. So I did one of the problems in the previous video, and I'll probably just get rid of that video because I didn't like it, but I'll just explain what I did here. So you need to do questions B and C on your own. I've posted the answers to that, okay? But if you're given an equation, C2H5OH plus 3O2 will go to 2 carbon dioxides and 3 waters. Okay, that's balanced. C2H5OH, what the heck is that? Look in your formula sheet when you were given chemical expressions, just chemicals, I guess, and you can look them up, okay? Because I'm only going to give you ones that are in your formula sheet. C2H5OH is ethanol. Okay, now ethanol has a heat of formation of here, let's just look it up. Ethanol is C2H5OH. There it is right there. Okay, ethanol. And it's got a negative 277.6 kilojoules per mole. And the numbers are negative. The numbers are going to be negative here, essentially because it has the potential to release the energy. There's a couple of ways you could explain that, but you leave them negative, okay? So look here, I wrote that, negative 277.6. Oxygen doesn't have a heat of formation. Carbon dioxide is negative 3 point, where is she? Carbon dioxide, negative 393.5. There it is right there. And water is at the bottom somewhere. There it is right there. Negative 285.8. You know what? You're going to use these same numbers every time you do a calculation like this, because you're always going to have carbon dioxide and water as your products. And the issue will be, well, how many moles of each do you have? Okay. So in this case, we have 2 carbon dioxides and 2 waters. So here is our formula, okay? We're looking for it's the heat of combustion, or basically the amount of energy in the reaction, okay? This symbol here, okay? But if you can see it, here I wrote it all out. It's the sum of the products minus the sum of the reactants. The products there's 2 moles of carbon dioxide and there's 3 moles of water. So there, I got those two numbers. There's carbon dioxide, there's water. So I carefully do those, and I put them in square brackets because you need to do the products all together, okay? And then you do the reactants. Now, of course, the reactants, there was only ethanol, and there was only 1 mole of that guy, and oxygen doesn't have a heat of formation, okay? So it's just the products are just the ethanol. So look, we get the two numbers, and you can see here I was adding something, but I really initially, if you caught that, initially I'm subtracting a negative, okay? So we have all of this, this first part in square brackets, minus a negative 277.6. These are all kilojoules per mole, okay? I don't try not to let those units trip you much. You're really trying to get these quantities. So then in the end, bang, here it is. The change in, or the amount of energy released in the combustion of ethanol is 1,235 kilojoules per mole, okay? Depending on significant digits, okay? So in the notes are the answers for the other two. So I'd encourage you to do those, okay? And let me know if you're tripping on them, but I think you can get them. So the last part here is dealing with thermodynamics, and it's just a quick review of the first and second laws of thermodynamics. First law is simple, just this, it's basically the law of conservation of energy. You can't create or destroy energy, and the total amount of energy in a system remains constant. And or you could say energy is always conserved, okay? Second law says, though, if you're ever converting or transferring energy from one form to another, you will always lose some of that energy to the surroundings, and it's usually heat. Okay, there's just nothing you can do about that. 100% efficiency is impossible. Now, we can come really close, though, so it's worth striving for, but you're kidding yourself if you're going to get 100% efficiency. And you'll see that in all the examples. So I know we've already posted an energy efficiency question from before. Here's another one. Just if you read a question like this, note the larger number is going to be the input. Okay, this 2.35 times 10 to the 7th kilojoules. This is 4.73 times 10 to the 6th. Okay, the larger numbers input, the smaller numbers output. You just go output over input. Bang, bang, like it shows over here. And we get 20.1%. Remember, you're going to get a ratio and you got to times it by 100, okay? Part B here says, what is the, to determine the percentage that is into non-useful forms of output energy. I wrote waste over that, okay? So yeah, waste energy is what they're talking about here. So easily you just subtract that from 100, right? Because everything has to add up to 100%. So if there's 20.1% efficient, then there's 79.9% wasted, all right? And what are those forms? It's basically just heat. That's what these last two account for, okay? You always will lose energy according to the second law of thermodynamics. Okay, so what I ended on here, which is really setting us up for section 1.4, which we'll probably get to later, maybe even after the long weekend. This is a coal-fired generating station. We have lots of these in Alberta. And with our coal supply, they actually crush it, so they get it to more of a powder because that combusts a lot more uniformly. But they burn that in a furnace, which is kind of shown here, not really. They're calling this here a boiler, but like underneath here, there would be kind of an area we would say is a furnace, okay? Because you're actually burning you got to burn the coal, and then that heat is hitting some pipes. And so the boiler would technically be kind of the pipes, because you have water coming in the pipes and that's turning into steam, which is, you can follow my little drawing here, the steam under high pressure goes into a turbine, which is basically just a propeller, if you want to think of it that way. And the steam pushing on that propeller makes it rotate. The propeller is connected to a shaft that's connected to a permanent magnet in most cases. And that permanent magnet will spin inside a coil of wire. That's what those, I kind of sketched my little red lines like this. So there's like coils of wire that are in the generator. That magnet spinning inside it induces or causes electrons to flow. They actually push the electrons in the wire and they make electrical current. And then that, of course, is put out through transmission using transformers and transmission lines. So the general conversion here is you start with chemical potential energy in the coal, and when you burn it, you release all of that heat and energy. And so it's really thermal energy that's released, but that then causes, it's really, I don't know, they're using kinetic energy. That's maybe an oversimplification, but because yeah, you have the movement of the steam and the movement of the water molecules that are now in gas form. They're not in water form. But anyway, that definitely, so we have a conversion from chemical potential energy to heat, to thermal energy, to kinetic energy, ultimately to electrical energy. And in this graphic, they kind of said everything was kinetic energy. And it's like, yeah, I guess you could say it that way. I like to separate it a little better in terms of the type of energy. So anyway, that takes care of the section 1.1 to 1.3. I did have this practice question, which is also posted. It's just what is the balanced combustion reaction for octane? And then what is the heat of combustion for octane? So take a look at that and let me know if you have any questions with that. But hopefully that's, I feel a lot better about this video because you can hear me. Okay, so keep up the good work, you guys.